Alright, this is our dynamics unit. In this one we've got three big ideas. First one is that objects and systems have properties like mass and charge, and that a system has internal structure. The next one is that the interactions of an object with other objects can be described by forces. And then finally the big idea number 4 is that the interactions between systems can result in changes to those systems. So, your learning goals. I want you to be able to predict the motion of an object or a system subjected to forces exerted by several objects. I want you to make predictions about the motion of a system of objects subjected to external forces. And I want you to be able to analyze a situation involving interactions among several objects using a free body diagram that include the application of interaction pairs to identify forces. Okay, so that's a lot. So first we need to talk about something called mass. We have two types of mass, inertial mass and gravitational mass. The inertial mass is a property of an object or a system. And what it does is it determines how the motion changes when it's interacting with other objects or systems. So in our previous unit we looked at net force, which is the sum of all forces. And when the net force equals 0, the object is in equilibrium, being that the object is either at rest or moving with a constant velocity. So what happens when the acceleration is not 0? So, the acceleration of an object, if it's not necessarily its velocity, is always in the direction of the net force exerted on the object. So the net force, which is a vector, would equal mass times acceleration. So look at this, the acceleration and the net force are always in the same direction. And that's because they're directly related. So the net force is directly related to the mass. We could say that the net force is proportional to the acceleration and that the constant of proportionality is mass. Also notice, not necessarily the velocity. The velocity does not have to be in the same direction as the acceleration or even the net force. So kind of think about a car while it's braking. The car is moving in a positive direction, but the net force is acting in a negative direction to slow it down. So the acceleration is acting in a negative direction. So if we were to make a plot of net force measured in newtons with respect to how much acceleration the object experiences, what we would observe is a linear relationship. So looking at this, slope and area are two important things. The slope would have units of Newton per meters per second squared, rise over run. A Newton is a kilogram meter per second squared. So on a force versus acceleration graph, the slope would have units of kilogram, which is mass. Area would have Newton times a meter per second squared. So that would be, I think, a kilogram times a meter squared per second fourth. I can't think of anything that's useful for. So area, in this case, probably doesn't have any significance. So, once again, notice that the slope of this graph is mass. As mass becomes greater, a larger net force is needed to have a larger acceleration. And that just goes back to the fact that acceleration and net force are directly proportional. So, looking at the graph, we can also say that when the net force is held constant, a larger mass leads to lower accelerations. So, the linear motion of a system is described by displacement, velocity, and acceleration of the center of mass. So that's something we've done a little bit, with the kinematics equations. That's what that's about. The acceleration then is equal to the rate of change of velocity with time. We've studied that. Velocity is equal to the rate of change of position with time, so we've looked at that. The acceleration of the center of mass of a system is proportional to the net force, so we've seen that. It's also inversely proportional to the mass. Basically, what that means is, if net force equals mass times acceleration, acceleration equals net force divided by mass. So we see that the acceleration is inversely proportional, 1 over m to the mass. Force and acceleration are both vectors. Acceleration is always in the same direction as net force. Let's put that into practice. Let's say we have an object that has 2 forces acting on it. This first force is 10 newtons at an angle of 20 degrees. The second force is horizontally at 30 newtons. The object itself has a mass of 10 kilograms. So, let's do a little bit of math with this. The first thing we can do is we can take this 10 Newton force and we can decompose it into 2 forces that are perpendicular. So the vertical component would be 10 newtons times sine of 20 degrees, and the horizontal component would be 10 newtons times cosine. And this should look familiar. We did the same thing with projectile motion, except it was a velocity we were decomposing. Now it's a force. 10 times sine of 20 is 9.1. And 10 times cosine of 20 is 4.1. So the first vector, I'm going to call this F1. I can write this vector as positive 4.1 newtons in the x direction plus 9.1 newtons in the y direction. The force, the 30 Newton force, I'll call that F2, and it would be positive 30 newtons in the x direction plus 0 newtons in the y direction. And now I can bring these together. So the net force, it would be 34.1 newtons in the x direction plus 9.1 newtons in the y direction. So if I were to draw that, it would look something like this. And then my net force will be the hypotenuse of that triangle. And I can find that angle. Notice that notice the arrowheads. You always put heads on your arrows. That's something they're going to look for on the AP exam. They want to make sure that you're putting the heads of your arrows so that you can show which direction things are pointing in. So looking at this, I can use a Pythagorean theorem, and I get that the net force is 35.3. To get the angle, I can just use the inverse tangent function. Opposite over adjacent. And when I plug that in, I get 15 degrees. And it looks like it's north of east. So that gives me the net force. Okay, now I can find the acceleration. The acceleration will be the net force divided by the mass. So the acceleration is 3.53 meters per second squared at 15 degrees north of east. And notice that because they're directly proportional, they both have the same direction. At this point, we now know the acceleration. I can start to apply my models I can start to apply my kinematics models. So if I were to give you things such as different positions or different velocities, we could then go through and do any number of kinematics equations. So that part's pretty simple. All right, that concludes video 1.